Thank you, and thank you for giving me an opportunity to present my work here. And today I'm going to talk about my work, which I've done like last 1.5 to 2 years with Chetan, Avinash, Dario, Sambuddha, and Bala. And
Is that working?
no, it's not.
Sorry.
Yeah,
Maybe battery is
yeah. No, I think he just changed the battery.
Ah.
I don't know. Or is there a? Oh, okay. No, I switched it on. Oh, thanks.
Thanks.
Yeah, and this is my structure of the talk. I first introduce these SYK-like tensor models, and I then briefly discuss about some numerical results, followed by some random matrix classification, which I will discuss. And then I'll go to the main part of the talk, which is to find the singlet spectrum. We'll propose a way to find it. We do it in 2 steps. Like first we diagonalize the Hamiltonian and find the eigenstates and eigenvalues of it. And then we'll see which combination of the eigenstates will lead to gauge invariant states. And then I'll conclude with some future directions. So let's start. The most complete definition of quantum gravity we have currently is via holography. And according to holography, gravity in d+1 dimensions and a non-gravitational field theory in d dimensions are dual descriptions of the same theory. Typically in all the holographic theories we know of, there is a large parameter n, and in the limit n going to infinity, things are usually under control perturbatively. But as of yet, there are no holographic theories where you can, with sufficiently rich dynamics, that are actually solvable at finite n. And this solubility at finite n is important to understand quantum gravity completely and to resolve problems like information paradox. And also, information paradox is related to the dynamics of the black holes. And to understand at least some aspect of the dynamics, we need to study a interacting theory in the bulk. And SYK model emerged as one such model where which can give some insights about these issues. And it was proposed by Kitaev based on an old work of Sachdev and A. And it is a quantum mechanical model with n Myron of fermions. The Hamiltonian is simply given by this. Here, this I power q by 2 is needed. It's a q interacting system. And this I power q by 2 is required if you want to make H Hermitian. And also these J's are picked from a random Gaussian distribution with mean 0 and this variance this. This variance is needed so as to have a good larger limit. And so why is this model interesting? It is solvable in the larger limit and at strong coupling, that is beta j much greater than 1, where beta is like roughly the inverse temperature or it corresponds to the energy. And this j is this j here. So basically you can solve it at, in the strong coupling limit. And also there is a emergent conformal symmetry in the infrared. And also this system is maximally chaotic. That is, it saturates the Maldacena-Schenker and Stanford bound. So the second and third feature imply that SYK model has a bulk dual which contains a black hole in it. So this is what, I mean, these are the reasons why it is interesting. And also one more reason is that it is fairly easy to study the finite temperature limit also, like this theory at finite temperature, as compared to say n equal to 4 superangles, which is really hard to study at finite temperature. This is much easier. But there is a somewhat of a problem with SYK because like while calculating the correlators in SYK model, we need to take an average over the entire ensemble of J. This is what we call disorder averaging. Because of this disorder averaging, SYK model is not unitary. And if our goal is to study something about the information paradox and all, this is not a very good model to study. And also this disorder averaging is necessary for the solvability of SYK and hence cannot be avoided. You can avoid, I mean, if you are avoiding disorder averaging, the solvability is gone. So it's a trade-off. And
I'll add one thing to that. If you know, SYK is supposed to be self-averaging. So suppose you take any given distribution of couplings, and leading order and larger is supposed to reproduce the same physics.
Okay.
And that theory is unitary.
Ah.
So you may say, well, why not look at that theory? And I think the answer to that question
Yeah,
is
I mean, if you mean saying that the J's you take as some fields and then
no, just take your distribution and choose from that a particular set of J's.
yeah, okay.
Choose your J's randomly, but they're fixed, and choose it from that distribution.
Yeah.
Now this model has an interesting property that it's supposed to be self-averaging.
Yes.
That is, you've chosen the J's this way. The law is that you will get the same behavior at large n for this one particular model as you would get for the average. Okay. So now you might ask, well, okay, I just choose some couplings at random. This defines a unitary theory. At large n is the same as the other one. Why don't I work with these?
Yeah.
Why it doesn't evade. And in my opinion, the answer to that question is that you see, it's really important that the SYK model is solvable in this ON singlet sector. And now, once you pick any particular set of couplings, there is no ON symmetry.
Yes, that's true. Yeah.
So that's very important. That's ON singlet. Nature.
So, but also this melonic behavior is like dependent on this averaging, right? Like some of the
averaging. But like I said, the law is, and maybe there's even a proof, that if you choose any for leading order at large, the physics of one particular choice of couplings is identical to the physics of the ensemble. So then you can use the ensemble as a trick for solving.
Yeah, that's true. Yes.
But
Yeah, thanks. So to address this issue, Witten proposed a model based on the work of Gurau and collaborators.
So just to say, the reason why you say, one says that there is no unitarity is that there is no Hamiltonian. Is that the thing? There's no.
Yeah, one thing.
Hamiltonian for the system.
No, one thing maybe like one thing I would like to think about is like it's like if you are computing any correlator, it's like taking average over multiple quantum systems. So at the end, it need not be unitary. Like it's an average of multiple quantum systems, and the final results need not be unitary. Like that's what I like to think about.
Yeah, I think exactly what you're saying, Gautam. If you ask what is the spectrum of the theory, what's the answer to that question? There's no answer.
What are the correlations of the theory?
Well, you can take correlation functions of any one coupling and average over it.
And then you can call those the correlation functions.
So then you can call those the correlation. But suppose you want the question, what is the spectrum?
But in the in quantum theory, finding correlators is fine, right? If you I think cluster decomposition might fail.
Possibly. Yeah.
Maybe, but you still would like the answer to the question. What is the spectrum of the theory? So finite dimensional Hilbert space at finite n should have a spectrum with delta functions.
Yeah.
Once you average, any particular set of couplings has that. But once you average, that goes away. It's clear that there is no answer to that question.
Yeah.
But is it true that the cluster decomposition fails?
I mean, I'm not sure. Like I didn't do anything like, but I think that cluster decomposition is based on unitarity, so I think that should fail.
Well, in all the calculations, it seems to work.
Yeah.
When the people compute 4-point functions, clustered in the right way, it seems to work.
Oh, okay. Oh, clustered actually decomposed properly. Oh, gotcha. Okay.
As far as I can. I think it's a more subtle kind of. Even statistical mechanical models, they violate unitarity, have cluster decomposition. Often.
Well, I was just thinking that in the quantum field theory, cluster decomposition would work, but now if you have a sum over a bunch of things, now when they go far away, it's a sum of products, which is not a product.
But each of them cluster decomposes.
Yeah, each of them does, but when you average, it's a sum of products now.
But it's a sum of things, each of which becomes like 2-point functions.
Yes.
Connected diagram is very small for each of them, so we cluster.
Yeah, each of them do, but
But then even in the average it will, because it will cluster.
the whole sum doesn't have to decompose it.
Well, for any one thing, it's product of 2-point functions when they're far away. Then you average, it becomes product of an average 2-point function. Yeah, maybe there's some subtlety.
Yeah.
Maybe. So cross terms meaning you're saying average of product is not product at all. Maybe.
Yeah.
Maybe.
But it seems to be
leading order in large n. There's no issue. Anyway, what you're saying sounds like a subleading order. maybe we can do it all.
But there would be same order because everything is disconnected.
But you know, at finite n, I'm sorry for all this.
Yeah.
At finite n, at large n, it's product and product that don't.
Yeah, disconnected.
Yeah.
Yeah, so everything would be disconnected.
Right.
Plus disconnected.
Oh, that's what you're saying. Plus disconnected the other way. Okay, wait,
Yeah, okay. Yeah, let's continue. Yeah, to address this issue, Witten proposed a model based on the work of Gurau and his collaborators on colored tensor models. This is the model we call Gurau-Witten model, and it is dependent on two integers, the small d and small n. In my talk, I'll make a distinction between small n and capital N. The capital N will be the total degrees of freedom. For Gurau-Witten model, this is d plus 1 into n power d. And the basic building blocks of the model are fermionic tensors, which are of this form. Here A is called the color index, and it takes values from 0 to d. And these i's are tensor indices of the gauge group, which I am going to describe. And these takes values from 1 to n. And, yeah. So how do you construct the interactions in the Gurau-Witten model? Like we say that the interaction term in Gurau-Witten model consists of d plus 1 fermions, and also the symmetric group we assign it as follows. Like for every distinct colors A and B, we assign a group ON AB. So because there are d plus 1 colors, the total symmetric group is a product of d into d plus 1 by 2 ONs. And the interaction term we write is a scalar under this group. And yeah, I'll just give an example to see these rules. Like for example, for d equal to 3, which is a quartic interaction, the symmetric group is a product of 6 ONs, and the Hamiltonian is given by this. And again, this factor is important for the large n limit, like appropriate large n limit. And if you see this Hamiltonian, you can see that every 2 fermions has only one common index, which is summed over, which is like following, which is actually the resultant of the rules I showed in the last slide. And also J is a dimension full coupling here, and so we set it to 1 in the further discussions.
Okay, so I was spacing on D equal to 3 is same as what Malthus called
Q equal to 4. Yeah.
So Klebanov wouldn't have this 0, 1, 2, 3.
Yeah, exactly. Yeah.
So isn't that a simpler thing to work with? I mean,
Yeah. I'm going to say that. Like first, I say that the next slide is about that actually. Yeah, give me one more slide. Yeah. So, like how is Gurau-Witten and SYK compared with each other? Like the large n perturbation theory of Gurau-Witten model has a similar behavior with that of SYK, which means that like in the leading term of large n limit, the both cases the Malonic diagrams dominate. And also like SYK model, Gurau-Witten model is also maximally chaotic. And here there is no disorder averaging, and this is one of the motivations to to introduce the model in the first place. And also there is a symmetry group here which can always be gauged to construct singlets, and the singlets have a well-defined description in the bulk. So that is about the Gurau-Witten model. And one more model which we consider in this talk is a model which is called uncolored model. This is a model introduced by Klebanov and Tarnopolsky. They suggested that we can define a model with a smaller symmetry group, but which have all the features of Gurau-Witten model. This is called uncolored in the sense that there is no color index here. And here again these i's are the tensor indices of the symmetry group, and each takes values from 1 to n. And also again for d equal to 3, this is a quartic interaction, and for d equal to 3, the symmetry group is On times On times On, and the Hamiltonian is given by this. If you see here again, like every 2 fermions has only one common index, which is summed over. And again in the further discussion, we always put J equal to 1. Also note that there are, you can write some other interactions which are scalars under O(n) cube, but those are not generally give you a Melonic diagram domination or something. Like this is one of the things which will give you a Melonic diagram domination, which we need like for comparing it to SYK. And also, if we quantize the theory, this will lead to the following anti-commutation relations. And as you can see, it is the Clifford algebra, like apart from a factor of 2, which can always be observed into these fields. So now in the rest of the talk, we propose a way to find the singlet spectrum. That we do in 2 steps. First, we propose a strategy to analytically diagonalize the Hamiltonian. Then we find which combinations of the energy eigenstates are gauge invariant under the corresponding symmetric group. So before asking about the spectrum of SYK-like tensor models analytically, we first do some we answer this question numerically, like for n equal to 3, which implies the capital N equal to 27. So because this size satisfies this Clifford algebra, we can always work, instead of working with the fermionic fields, we can always work with the gamma matrices.
Sorry, before, are you doing it for the full interacting problem at the moment?
Yeah.
So before we do that, and maybe you did this in one of your papers, there's a question just in the free theory.
Mm-hmm.
How many singlets are there in the free theory?
Oh, I mean, it's actually computed by Klebanov and all. Like it's not a I mean, at least I don't completely understand their computation, but it actually has been computed. Like,
is it a lot or not too many?
Yeah, it is. Yeah, it is a lot. I mean, like,
okay.
See, it is like it's much smaller than the. I mean, there is an ungauged model and the gauged model, right?
Are we dealing with the gauged model?
Yeah, I mean, I'm just saying, like ungauged model, the spectrum goes. I mean, the Hilbert space dimension grows very fast.
Yes.
And even the singlet sector, it grows fast, but not as much. Like I can give you the precise formula. I can look at it and tell you. Like I don't remember. Yeah, to compute the number of singlets, you don't need to deal with interacting terms and all. Just the kinetic part is sufficient.
So the total number of states in the ungauged model, in the free theory, they're all degenerate, I suppose.
In the free theory, yeah.
Hamiltonian 0.
Yes.
And the total number of states in the ungauged model would be, what is it?
Some 2 power n by 2.
2 to the power n cube by 2. Right?
N cube, yeah, whatever.
Right, exactly. So does the number of singlets also scale like 2 to the power n cube, or does it scale more slowly?
More slowly.
Yeah. Okay.
Singlet with respect to?
All 3 SONs.
Yeah, with respect to all the O(n) cube.
I mean, if there is no interaction, then it would be a bigger symmetry group, right?
Yeah, but we.
O(n) cube rather than O(n) tensor.
Yeah, that's true. But we want to consider. I mean, like our goal is to find the singlets of this. Like say, for example, whatever the Klebanov model, uncolored model, or Gurau Witten model. So we want to compute the number of singlets there. So we consider the singlets only of that group. Yeah. Yeah. In principle, yeah, what you're saying is true. Like there's a bigger symmetric group if you're considering only the kinetic term. Yeah. So what I'm saying is that because these size satisfy Clifford algebra, we can always assign the gamma matrices to this size, and then we can diagonalize the Hamiltonian numerically. So, and if you diagonalize the the Hamiltonian, and we plot the density of the states, it will look something like this. From here, you can see that the spectrum is symmetric around E equal to 0, and this is called what we call spectral mirror symmetry. And also, you can also find that the entire spectrum has a 8-fold degeneracy. Like all the energy eigenvalues has at least 8-fold degeneracy. This this can be explained using finding some discrete symmetries in the problem. Also, we showed that n equal to 3 uncolored model has some signs of chaos. The diagnostics we used are level repulsion plot and spectral form factor. I'm not going to the details, but those are the things you check for seeing whether the system is chaotic or not, and n equal to 3 uncolored model passes those tests.
So in your plot, what have you taken the various parameters to be?
This one?
Yeah, how much is n? This n equal to 3?
27, yeah. Yeah, capital N equal to 27 or small n
And
equal
j
to
is frozen to be 1.
Yeah,
of course.
j is chosen to be 1. Yeah.
And the two limits are
this one and this one?
Yeah.
I mean, this is supposed to be the limits as in like, this is supposed to be the ground state, like the lower energy things?
Yeah, so I'm saying that suppose you know, this is some kind of a semicircle or whatever it is in the continuous.
Yeah, I mean, that I'm not, I mean, that I'm not completely sure.
Where this minus 130, that number comes from. Is it?
Oh, this is simply by diagonalizing. These are the energy eigenvalues.
I agree, but is it like something times root 2?
Oh, that I'm not sure actually. Like,
Okay.
yeah, but also I don't know whether these will satisfy the Wigner-Semicircle law, because the ensembles we encounter here are not the standard Wigner-Dyson ensembles. Those are some extensions of Wigner-Dyson ensembles. So maybe it is still semicircle law, but I'm not sure of it.
Near the, I think this rho of E, the density of near the end points.
It should be semicircle. Yeah, at least for SYK it is, yes, that I know. But
for SYK. So
yeah.
I don't know what happens here.
Yeah, this I'm not sure actually.
How many states do you get?
Here, this is only 8,000 states here. It's not much.
And let's compare that to 2 to the power 27 by 2, right?
So, yeah, which is 2 power 13, which is like 8,000.
That's 8,000.
Yeah.
So this is with the singlet constraint or without it?
Without.
Without. And how, do you have a similar graph for with the singlet constraint?
With the singlet, like this model doesn't admit any singlets, because I am going to explain, like whenever n equal to, n is an odd number, there are no singlets.
Okay.
So
that's a drastic cut.
yeah, but if you are going to n equal to 2, there are only 2 singlets,
Okay.
which doesn't show anything. And but for n equal to 4, it is difficult to solve. But
You can count the number of singlets. Right?
yeah, you can count. And the counting is there is only 36 singlets in n equal to 4.
It's a huge cut down.
Yeah, huge cut down. But n equal to 6, it's much more. Like it's like order of magnitudes different. Like
Just a side comment. If you remember in our paper, we had to make a Fermions complex. Otherwise, we got almost very few states.
Yes.
That's what they say.
okay.
So n equals 3, you say there are no singlets.
Yeah, that I am going to explain why.
The interaction operator was a singular operator.
No, I'm talking about singlet states. No, operators you can construct, but
What's the difference between even and odd dimensional gamma matrix?
there are no singlet state. Like if you're considering some states and you gauge the group, then all the singlets will go away. Like
This is irrespective of the interaction.
yeah, it's like all the states are charged under the singlet, under the gauge charges. That is easy to see. I'll explain.
So this huge number of cold stones that you got, you could get them only for the complex part.
No, I think your argument should work in real also, right? I mean, there
Yes.
is.
It was the second part of our paper that works with paper complex. We did a counting of states.
I see.
Yeah. The first one I think should work.
Yeah, I mean, I don't see a reason like why it should change.
Oh, okay.
Yeah. So before going further about finding the
About p equals 0, that's not, that just.
yeah.
How does that come about?
Yeah, okay, let me explain that. So, say for example, if you exchange these B and C everywhere, like the second and third index everywhere, the Hamiltonian goes to minus of itself, and you can always construct such operator. Like you can always construct an operator which exchanges these two indices. Like yeah, I mean, I can show you the actual forms like we have it in the paper. Like I am not putting it. And
Discrete symmetry.
yeah, that's a discrete symmetry. Yes.
Is it the analog of gamma 5 when you have even?
No, gamma 5 I think commutes with this, because there are 4 of them. I mean, whatever you have, so it always commutes. It's a somewhat a complicated operator, that's why I didn't put. Yeah.
No, but that's what he's saying. He's saying if you have a state and you act on it with gamma 5, oh sorry, you have EL and minus E.
Yeah. Yeah. So before going to the finding the singlet spectrum, we described some random matrix classification of these SYK-like tensor models. So the basic conjecture of quantum chaos is that the eigenvalue statistics of quantum chaotic systems is same as that of random matrix ensembles. And this is not a proven thing, but there are many examples which satisfies this conjecture.
Sorry, not able to visualize. Can you show how a typical singlet looks like for even n?
Yeah, that I'll show. I mean, that I'm going to show.
Just be the indices contract.
Yeah, but before that, we need to construct a basis.
For O n to the power 3
Yeah.
or 4.
Yeah, whatever, yeah.
Isn't it the following mathematical question? You have a spinner of SO whatever, n cube. And how many components of that spinner are invariant under O n times O n?
Yeah, yeah, that's true. Yeah, exactly.
Under each SON, it's an irreducible representation.
Yeah, one spinner will decompose into many reducible representations, and you want to spin singlet.
Wait. Oh, it's a. Oh, when you say SO n cube is in the space.
Yeah.
Yeah.
So SO27 is irreducible to the representation decomposable.
Yeah, SON times SON times SON. Whole cube, yeah.
Fine.
Yeah, anyway, I'm going to show some singlets. Yeah. And the particular random matrix ensemble depends on the symmetries of the specific Hamiltonian. The important point is it only depends on the symmetries of the specific Hamiltonian. It doesn't really remember all the details of the Hamiltonian and all. And for instance, for SYK model, with different n belong to standard Wigner-Dyson ensembles based on the properties of time reversal operator. Like you can construct a time reversal operator which is a symmetry of the SYK. Depending on the properties of it, you can actually find which SYK models belong to which random matrix ensembles, and those belong to standard Wigner-Dyson ensembles. So in the case of tensor models, they belong to a larger class which is Andreev, Altland, Ginberg classification. This is an extension of Wigner-Dyson ensemble, Wigner-Dyson classification. This is because there is an extra symmetry in the problem which is a spectral mirror symmetry. Also, to identify the ensembles of tensor models, we find this S and time reversal operator T, and the ensembles can be classified using the values of S square and T square. And this can be done for arbitrary n and for quartic interactions in the case of uncolored models. And the same thing can be done for arbitrary interaction and arbitrary n for the case of Gurau-Witten model. This is just a technical simplification. We don't really understand why this is happening here, and we can't do it here. And these are the various ensembles. The details are not really important. So
Which one is Wigner-Dyson?
here there are no Wigner-Dyson. Wigner-Dyson are this standard, this Gaussian unitary ensemble, orthogonal and symplectic ensembles.
Those are not part of it.
Yeah, those are not part of you.
Sorry, how do you make such a classification?
It only depends on the values of S square and T square. Like the classification is that if you have this S square, this T square, this is the class.
Please, I'm sorry, but remind me what was S square, T square?
S square is the you compute the S, which is a spectral mirror symmetry operator, and take a square of it. Because everything is roughly gamma matrices, the square of them will go to either +1 or -1.
Yep.
And similarly, the T square too.
And how do you know that these are the things that classify? What is the principle? Where does all this come from? They are assuming there's some universality, right?
Yeah, this is a universality. Yeah.
Why? Why is that?
Basically, the conjecture, what it means is that after, like, if you wait, if you take a chaotic system and wait for sufficient amount of time, it will forget about all the initial details. Like the system really doesn't remember anything about the theory we started with, and it depends. And in that sense, it becomes universal. Like you don't need to know the theory specific details to understand, like at late time how the system behaves. So
you're saying the spectrum of almost any
quantum chaotic
system.
Chaotic system. Yeah. I mean, yeah.
But most systems are chaotic.
Yes.
Right?
Yes.
So almost any quantum system in some large n limit is characterized
And large timed.
But spectrum doesn't know about time, right? Suppose I just want the spectrum. You're saying the spectrum of any almost any quantum system is characterized only by some symmetries.
Yeah.
I see. That's a true statement. That's not a statement I'm aware of.
But I think there are
No, I think that, no, but somehow the large time is also important.
Well, if I ask this
I don't know.
spectrum,
No, it's not.
No, no, there is no time.
There's no time.
The
Right.
Bayes conjecture, this was like a quantum chaotic system, Bayes and some others, they say that it should have the following property. It's a very complicated Hamiltonian, so therefore if you diagonalize it, then the eigenvalues of that Hamiltonian, the eigenvectors, excuse me,
Mhm.
eigenvectors of that Hamiltonian with respect to a fixed basis of vectors, okay, are like random vectors.
Oh, okay.
Now, if the random vectors without any symmetry in position,
Mhm.
then it should be like the Gaussian
Oh, okay.
random. I mean, the eigenvectors of the Gaussian random vector.
Oh,
As a
actually.
result,
Okay.
the features of the theory
Oh.
will be like that.
And a similar statement for eigenvalues.
A similar statement for
Eigen- And there's no time.
which
Like,
is the eigenvector statement is more powerful.
Right.
yeah, I was saying, yeah, I mean, I don't know. Somehow I got mixed up with large time
No,
because.
with that, the stuff about thermalization and other things, you can often do that.
Oh, okay. Okay. Yeah, thanks.
Here we don't assume any further symmetries to the
Uh,
So presumably
Yeah.
here, if there are additional assumptions, then what happens to this conjecture were worked out by this Altland and company? Is that the
uh, I understand. Like, can you repeat the
So
question?
now you say that, okay, so now you have additional symmetries, like
Yeah,
these
yeah.
two Z2 symmetries,
Yes.
and then
Yeah, then it is like.
the eigenvectors of course cannot be completely random.
Yeah, I mean,
They are random up to those symmetry
Yeah, so-
constraints.
no, I think it's like the Wigner-Dyson ensembles are like 3 in number, like say Gaussian, unitary, orthogonal, and symplectic,
Yeah.
and this is a 10-fold classification. Like it, what do you say? It is like an extension of this Wigner-Dyson. Like if there is no spectral mirror symmetry, it reduces to Wigner-Dyson. But if there is a spectral mirror symmetry, you need to talk about this classification, which is an extension of this. So
There is some matrix ensemble that has, there's a matrix model you can write down with
yeah,
this universal answer.
yes. At least if you, I think there's a paper by Ludwig Yu and Xu, like where they compute this something called near space distribution. Like you take all the eigenvalues, make them in an ascending order, take the differences between the spacings, and then compute a distribution for that. That for if you do it for SYK, that matches with some of the Wigner-Dyson ensembles, like that they showed. So,
No, but just to repeat this question,
Uh-huh.
are these things some kind of matrix models? This Altland or whatever? There's models. They belong to some classification. So
Yeah.
these classes are characterized by what? They are characterized
Uh,
by some.
yeah. For example, if you are talking about, say, one of the Wigner-Dyson ensembles, you just give the probability of, let me write it.
Yeah, so that's the story about Wigner-Dyson. And about
Yeah.
these guys.
These guys, I mean, like, I don't know the specifics. I think I assume that it would be the some extensions of this. Like, I'm not. Again, here also, I think there would be given the, I mean, probability distribution for each of the matrix elements there. Like some here we are giving the distribution for matrix elements, various matrix elements in this form. In the same way, I think we would give the matrix, I mean, the probability distribution for various matrix elements using some distribution.
So there is a matrix model.
Yeah.
But still a single matrix, is it?
Mm,
Must be some family,
Yeah.
otherwise
yeah, I mean, these matrices are distributions, right? I mean, I don't know how much you call it a
Matrices
single.
are all given by some, so it could be real matrices or Hermitian matrices.
Yeah,
etc.
depends. Yeah.
And some people had played with quaternionic matrices also.
Yeah, those are called symplectic ensembles. Yeah.
So I don't know too much about them, symplectic
Yeah.
stuff. But I thought that was the end of it. What else is left?
No. Yeah, I mean, we just presented it because we thought that finding these universal classes are useful for, like, if you want to study about I mean, I don't know exactly, like if you want to study about the properties, more about the properties of these tensor models regarding quantum chaos and all. But apart from that, I'm not an expert in this. Like after this we stopped, like we didn't work much on this. We just want to give the universal classes for everything. Yeah. Now we move to the main part of the talk. And the first step, we'll propose a strategy to diagonalize the Hamiltonian here, and we demonstrate this method for even n case and for uncolored models, and it can be extended to other models via some modifications. And so the first step to finding the eigenstates is to start constructing a basis. The basis we use, we first start by defining the creation and annihilation operators as this, and here this k plus or minus takes values from 1 to n by 2, and it is related to k as follows. So this k is always odd integer, and this is always even. And from the anti-commutation relations we have previously, these creation and annihilation operators will satisfy this commutation relations, and also in the terms of these new operators, the Hamiltonian is simply given by this. And yeah. And now we define something called Clifford vacuum.
Sorry, if you could just show me your k and k plus 1. Thank you.
Okay. Yeah, for odd integers, if n is odd, this will be slightly modified, but yeah. Now we define something called Clifford vacuum, which is a state that is annihilated by all the annihilation operators. And
K minus, I'm sorry, you made a thing out of k and k plus 1 plus minus.
K plus minus, yeah.
So now k runs from 0 to n.
1 to n. K runs from 1 to n. K plus or minus runs to 1 to n by 2.
K plus minus runs, yeah. So that index, I and j run from 1 to n, and the last index runs to n by 2.
Yeah, yeah.
Okay.
Yeah. Now we can construct the entire representation by acting with creation operators. So for example, at level R, a generic state would look like this. And also we know that the total number of creation operators are n cubed by 2 in number, and this implies that the Hilbert space dimension is 2 power n cubed by 2, which is as expected. And also after a paper appeared, and independently, these states also have been used by Corcolu and Maldacena in the context of SYK for other purposes. These are called, which are called pure states in their notation.
Where they don't use this k plus k minus thing, they call 2k.
Yeah. Yeah, we could also have done that, yeah.
But wait.
Yeah.
Are you imposing this only for k minus thing, or don't you need to do psi of I minus j minus k minus?
We don't need to.
No?
No, this is sufficient. Because if you see that, for example, one of the checks can be that we obtain the total Hilbert space dimension correctly.
You just have to pair the whole set of all oscillators, you have to pair oscillators. Right, so in the whole set of n cube gamma matrices.
Yeah, I see.
Yeah.
There's a pairing.
Yeah, this is like a Clifford representation if you think. Yeah, initially actually we started with that, we put everywhere minus, but that turned out to be cumbersome.
No, I understand. So there's a big Clifford algebra with all the fermions and this.
Yeah.
So you could be perverse and just choose any two gamma matrices and then do this.
Yeah, you can, but
Any pairs.
yeah, but that will be, I mean, we wouldn't have any organization principle then, like.
Does this symmetries say something universal about operators which thermalize in large J beta limit?
Sorry, can you repeat the
You have
question?
many operators.
Yeah.
Then you can look at their Fourier sum functions.
Yes.
And then you can ask if there is any chaotic behavior, or does it
You mean something computing like something like OTOC or something, or?
or chaos. And then you can also ask about if you want to talk about thermalization of these
Yeah, we can.
operators.
Yeah.
Now these are some concrete symmetries present at all finite ends. All finite values, right? But
Yeah.
then you can also, you can, in particular, you can go in the other limit, where n is large and where J is large.
Yeah, but our goal is to do it in the finite n.
But
Because
since you have a finite n, does these symmetries say something
you mean
generic at let's say you are doing at finite n. I am
Which
interested in
symmetries are you looking for?
Yeah.
He has
Start conjugation, those guys.
the two G2
Yeah.
symmetries that he has.
okay.
Those. You are doing at finite n. I just want to look at large n and large bit J.
Yeah, large n, I don't know how to first compute the spectrum.
But the argument of existence of symmetry.
Yeah, that shouldn't be a problem. That doesn't depend on n, but yeah, those symmetries still exist. Yeah.
Something generic or something.
I mean, it just says that the spectrum is symmetric around E equal to 0. So you want, I mean,
No, I think
is
he's
this
asking whether there is some kind of subclass of operators which mix within themselves.
Yeah,
That will
something
of course
like that.
happen.
yeah, that would happen. Yes.
Because Hamiltonian results go. So there
Yeah.
are two Z2s.
Hmm.
It's like minus operators will only mix with themselves.
Yeah.
Minus plus minus and plus.
And then does
That's
they say
the
anything
problem.
anything important about the coupling to the Schwarzian? Something like that, like some universal. Maybe this is a question I should answer later, but
Oh,
this is
yeah,
the
I'm not
question
sure.
I'm asking.
I'm not sure. So, yeah, as I was saying that this is the generic state at level R, and so next we talk about like how to find the spectrum. Before that, we see that there is a simplification. Like we define something called level operator, which counts the number of creation operators in a particular state, and the level operator is defined by this. And the important thing is that the Hamiltonian commutes with this level operator. So we can always find the eigenstates level by level. So which is a good simplification, at least for the low lying levels. Like so we can find the eigenstates at low levels. So once we know this fact, and
this is the conserved quantity with the interaction. It
Yeah,
commutes with the Hamiltonian.
yeah, it does.
For arbitrary interaction.
Arbitrary interactions, I am talking.
Arbitrary values of J, right? It does not.
Yeah,
care
it doesn't
about
depend on J.
What is it in just always I will ask this
Yeah,
question.
I'm always putting J equal to 1
Yes,
in the
so
entire discussion.
Is there an identification of this operator in those limits where J is large? I am always interested in this limit.
J large.
J is large and n is large. What is this operator? It looks like an exact conserved quantity.
Yeah, it is the exact conserved quantity. I mean, I'm not getting like what you are exactly asking. Like
This is the conserved quantity.
yes.
Now
It doesn't depend on J, for example. Yeah, we can take. I mean, it doesn't depend on J or n.
This is why I am saying because it does not depend. So I can take n large
Yeah.
and I can take d pi ultimate.
Mm-hmm.
And then if I ask what is this operator look, how does this operator look like? How it acts
You mean in
on
the bulk?
coefficient function? Does it say something? It is a symmetry operator, not some exact
Yeah.
symmetry operator.
Yeah, one. I mean,
Okay.
I don't know. I'm not sure about that limit.
Okay, I have some. This guy commutes with the level operator. I mean.
Yeah, you can just see it, but because see, for example, for every plus, it will give you a plus, and for every minus, it will give you a minus. And if you see the Hamiltonian, there are 2 pluses and 2 minuses. Like that is like very crude way to see.
It's the summation over all ij and
Yeah,
that
yeah,
level operator.
yeah.
I see. You can write the Hamiltonian in this fashion.
Yes.
This is unfamiliar from SYK.
Yeah, in
Because
SYK, I think
SYK,
you
I
can't.
can have quatic Fermion products which are like psi 1, psi 3, psi 4.
Yeah, that is, yeah.
I mean 3 odds and 1 even.
Yeah, which is not the case here.
Yeah, which would not commute with the.
Yeah, here it is not the case. For the tensor models, you always have say, for example, if you are considering 2 odd numbers, say gamma 1, gamma 3, the other should also be either, the other 2 should be either odd or even. Like
So
it always comes in pairs.
So the spin eigenstates
Uh-huh.
of Kurkulu and Maldacena,
Yeah.
I mean, the eigenstates of this level operator thing, they are also eigenstates of the Hamiltonian.
Oh, yeah.
I see.
Yeah. Here, yeah. I mean, you are.
No, I'm talking about your.
Here,
There
yes.
I know that they are not.
Okay. Here,
The
yes.
spin eigenstates are not eigenstates of the.
Oh, okay. Yeah, but here it is. It is the case. Yeah.
I see.
Is
surcharge a subgroup of the third SON? Suppose I take your n is even, so I divide my n into m and m, and I do a alpha rotation in the top half and minus alpha rotation in
that
the
makes
bottom
sense.
half. That seems to moderate.
I think so too. Yeah.
I mean, it feels. Why were there equal pluses and minuses? It's because of the SON.
Yes, exactly. Yeah.
Yes. So this is some subgroup, I think, of that. No, I don't think so. Yeah.
Okay. In tensor model, the SON symmetry
is
is
that?
manifest.
Yes.
Without doing the disorder averaging.
True. Yeah.
I mean, suppose it had been SO2. The SO2 invariance would have been that there are as many pluses and minuses.
Yeah. Exactly. Yeah. That's true. Thanks.
Okay. Yes.
But it's just about a statement of equal number of plus and equal number of minuses. Nothing more, not more than that.
Not more.
No.
And therefore, it should not have any great implications when you put the singlet set. Yeah. Okay.
Yeah. So once we know this fact that the Hamiltonian commutes with the level operator, and if you see the form, there are two minuses here. So all the states at, say, the Clifford vacuum by itself is a eigenstate, and all the level 1 states are eigenstates of the Hamiltonian, because they just annihilate it. The Hamiltonian just annihilates it, and the constant part just remains. So so we have found some eigenstates already just by using this fact and the form of the Hamiltonian. And to find the eigenstates at the higher levels, we use Young tableau. Like, before doing that, we just set up our notation. To start with, we note that the psi ij k plus transform under fundamental representation of O n times SU n by 2. This is SU n by 2 because we broke that symmetry while defining these things. And in Young tableau language, we denote this psi ij k plus as this, all the fundamental representations. And so at any level R state is just obtained by taking tensor products of R fundamental representations. So for example, all the level R states are given by the irrefs present in this. I'll just explain the notation, like how we denote the states. The states are denoted by R1, R2, R3, where R1 and R2 are these are like irreducible representations of, say, ON1, ON2 and SU n by 2. Say for example, consider this is one of the states. Say, by this I mean that you take psi I1 J1 K1 plus I2 J2 K2 plus, symmetrize I1 and I2, symmetrize J1 and J2, and anti-symmetrize K1 and K2. And doing it explicitly will give you this. Say for example, you can notice that this and this line are the same apart from a overall minus n. Like for example, this term here and this term here are the same, but there is a is it the same? Yeah, these are the same, but these are exchanged, like this went here and this went here because of the fermionic, because these satisfy Fermi statistics. This state is not 0. Like for example, instead of this anti-symmetrization, if we had a symmetrization here, this would have been a plus and the anti-state would have gone to 0. Like I'll discuss more about this later, but yeah, the main point I want to make here is that this notation implies just symmetrizing and anti-symmetrizing things. Even the representation becomes bigger, the same thing holds.
Wait, the vacuum.
There should be a vacuum here. Like
the vacuum of this Clifford algebra is, how does that transform under?
It transforms non-trivially under ON cube,
yes,
but it transforms well under ON times SU n by 2. It's an invariant of ON times SU n by 2.
Okay.
So now suppose I just wanted to look at the SUN singlets.
SUN singlets.
And SUN by 2.
Yeah.
N by 2 singlets. What your whole spectrum is built by building M fundamentals, acting on an invariant vacuum. Now there are no singlets unless M is equal to a multiple of N by 2.
M is a. That is one of the reasons. Like if you are want to construct a singlets with respect to the final ON, you always need a epsilon symbol, like epsilon times S n by 2.
There is exactly one singlet.
No. Why is that?
Because your level cannot exceed N by 2. I'm from this example.
No. Like for example, you can have.
Because there are many other indices.
Yeah.
So you have.
And also the singlet level is some n cube by 4 or something. So there are multiple epsilons you can write.
I see. Wait, what is the maximum level that you can have?
N cube by 2. And the singlets are at n cube by 4.
No, I'm sorry. Let me ask.
Lots of these things, lots of variants.
Lots of variants. Yeah, that's
Exactly. Yeah.
Flavor indices.
Yes. Yeah, it's very much. This problem is very much similar to.
Yeah.
At least the constructing of this antisymmetric states and all
Yeah.
is very much similar to the baryonic wave function construction.
Yeah. So it's basically in the SUN sector you use. It's only the ON times ON that measures it, right?
Mm.
Even the SUN sector, because you can go all the way to n cube, like
No, N by 2.
No, n cube by 4.
Yeah.
No, it is basically written like this.
Level is n cube.
This is n by 2, and there are multiple boxes.
The level,
I
the
think this
size
is-
that you can have is n cube, right?
Yeah.
Yeah, for example, in the Young tabular language, you can do it.
I understand.
Yeah, okay.
But basically it'd be multi-baryons.
Hmm.
Baryons and then
Yeah, it is slightly complicated than baryons in the sense that we know that baryons are color singlets. So we, in principle, we have only 2 quantum numbers to play with, but here we have 3, which makes things complicated.
Yeah. Okay, I understand.
Yeah.
We can have these elementary diagrams where only there are just n by 2 indices. Then
Mhm.
we can have multiples of that.
Ah, yeah.
That's
Yeah.
what it's called.
Yes.
Fox space of that.
Yeah.
But then why is there, I still don't understand why is there no symbol?
Oh, that I'm going to explain. Like,
In the odd case.
yeah. I mean, you can see it by.
Can you do n by 2?
No, you can one way to.
N by 2 and there's one more gamma matrix.
Yes, exactly. Yeah.
And that probably is.
Yeah. One other way to see is that the singlets are at say n cube by 4th level. Like if n is odd, this is a fraction. So it doesn't have anything.
Already when you were saying SUN by 2, what do you mean there?
No, n is even. Like here the entire thing I'm talking about, n is even.
Oh, here as you did that.
Huh?
You made that assumption.
Yeah, I made that assumption. Yeah. So before, to find the action of the Hamiltonian, we note the following identity. This is easy to prove. The details are not important. I just want to see that this is a simple identity. And the Young tabular version of this identity will lead you to the finding the action of the Hamiltonian.
There's a fierce identity.
This is the Fierce identity.
I think so. It's a real and
No.
gamma matrices.
There should be some spinors also, right? Fierce identity has spinors also. Right? Maybe this is.
And which these days would spin.
That's also a possibility. Yeah.
This singlet that you were talking about is ON, right?
Hmm. Yeah, I didn't come to the singlet part yet.
But here you were talking about SUN by 2, the subgroup.
Yeah. See, this is just a basis. This is a convenient basis. We are arranging everything.
Okay.
We don't really have any basis. We didn't find any other basis which is comfortable to work with. So at the end, we find the singlets of ON times ON times ON. Like this is just a basis we are using. Yeah, in the Young tabular language, the action of the Hamiltonian on a generic state is given like this. And also this H prime is that I just remove the constant there and just put it in the H. And by this dot we mean the traces. And and also there's supposed to be a Clifford vacuum here, which I forgot to put. And the important thing to know, once we have this equation, the immediate question is like how can we find the eigenstates? To do that, first we note that the Clifford vacuum is invariant under ON times SUN by 2, and also the H prime is also a singlet under ON times SUN by 2. So to find the eigenstates, we just compare the representations here and representations here. And also note that the representations which are coming on the right hand side are like a subset of the representations which are present here. So some of the eigenstates are have a 0 eigenvalue, obviously. And, so what we have done essentially is that we rephrase the problem of finding the spectrum into a well-defined group theoretical problem. Like if you can find all the representations, we know all the eigenstates. And also by comparing the representations, we can also find the eigenvalues. So, yeah. I'll just give an example like.
Sorry, I was spacing out. Just can you show me the spectrum in terms of representations again?
Which one? This one?
That's the answer. So
yeah, this is the action of Hamiltonian on a generic state. You take a generic state, act with the Hamiltonian, and you use this identity. You can write it like this. And the thing to notice is that there is a Clifford vacuum here, which is invariant under O n times SUN by 2. And this H prime is also invariant under O n times SUN by 2. So to find the eigenstates, we just compare the representations. Like each representation is eigenstate. Each irreducible representation of this O n times SUN by 2 is an eigenstate.
And these come with zero degeneracy?
No, there is degeneracy. I mean,
so
there is degeneracy here.
Wait, are you saying that the whole action of the Hamiltonian is some Casimir or something?
It's not Casimir, right? I mean, this.
When you have a degeneracy, do you have to take particular linear combinations or any linear combination?
Degeneracy, you mean like degeneracy in the eigenvalues, right?
Degeneracy of representations of O n times SUN by 2.
Degeneracy of representations in the sense like.
If you have five of the same kind of representation.
5 of the same.
Well, but what I understood about your argument was that you had some argument which I didn't completely follow, but it was like that if you've got something that transforms in a given representation, action of the Hamiltonian will preserve that representation.
Yes.
That's great.
Yeah.
Now, there may be many states that transform in the same representation.
Yeah.
Then Hamiltonian will mix among them.
Yes.
Nontrivial.
Yeah. Exactly. Yeah.
That you have to take care of.
Yeah, that I have to take care of.
Okay.
But that generally happens only at higher levels, like which is really hard to compute. So, like I'm going to talk about it anyway.
I'm sorry, just the left hand side here is an R-fold product for.
Preserves these representations.
So it's an R-fold product in all the slots.
Yeah.
If you had two or more, then you
It is just right.
That's how you take it.
one copy.
Yeah, I mean, that state is simply like say psi I1 J1 K1 plus 2 psi IR JR KR plus. It's the same thing. This I'm writing it like that.
And in particular, you told us at some point that there are many singlets. So if there are many singlets at a given level, then you have to do some work to find.
Yeah, all the singlets are at only one level.
Which level is that?
N cube by 4. The mid level. Yeah.
That someone should have been obvious, right?
Is it?
I said that I was just talking about singlets of SUN by 2. He's now talking about singlets
Yeah.
of the whole thing.
Yeah. O n cube. Yeah.
Yeah. It's much more complicated.
Yeah.
And it's mid level of the whole thing, not of.
Also, I don't think you said you're saying Hamiltonian preserves the representation.
Yeah, because Hamiltonian is a singlet under O n times SUN by 2, and these are representatives of O n times SUN by 2. It doesn't change. So if there are same representations, as Shira was saying, like then it mixes.
But what is this dot and
No, dot is simply a trace. Because we are dealing with ONs here, there is a trace. So for example, there is no trace in case because it's SU.
So in the case, just to be clear, just for the singlets, the 36 singlets or whatever, there you'll have to solve some complicated 36 times 36 Hamiltons.
Yeah. I mean, to find the singlets is a different problem, but you are saying that.
To diagonalize the Hamiltonian in space, you'll have to, there'll be a 36 times 36 Hamiltonian, you'll have to
Why is the right hand side any simpler than the left hand side? I mean, what does this?
No, I'm just saying that this is a.
by you?
Sorry?
How do you use this identity?
I mean, I am just using this identity to write this.
I agree.
Yeah.
I agree. So you have some expression like psi I1 J1.
Oh, okay. This one.
And then the right hand side would be some.
Yeah.
stuff,
I'll write for this part.
Yeah.
This would be say psi IP. Q. Psi. So this is yeah, these two are summed over. This is traced over, and this JQ is coming from there, and this KP is coming from there. You just take the first ones here and write on the first one, and take the second ones and write this, and remaining things you write. Like for example, here you can see.
And take the tensor product of that with
this.
The same stuff with.
No, the P and Q omitted.
Two folded products.
Yeah, exactly. Yeah, I'm going to talk about it.
I see. So what you have achieved is to write a bigger tensor in terms of a smaller, bigger space. It's kind of a contraction, is it? Or I don't
Yeah,
know
it is. See.
What is this doing for you?
Yeah, this is the action of the Hamiltonian on this will give you this. This is the action of the Hamiltonian. And to find the eigenstates, we are comparing the representations on the left hand side and the right hand side. Those will be our eigenstates. I'm going to tell you, I'm going to talk about n equal to 2 at level 2. You will see what I mean. Yeah, so we now construct the eigenstates at level 2. And here n is arbitrary, like this is true for any n. And so the action of the Hamiltonian on this state is given by this. This is just a technical detail. And in the Young tableau language, the left hand side has in this form, like I'm just expanded the tensor products. And here like various states corresponding to choosing each one of them. Like for example, if you choose this will correspond to a state. And say this, and this will correspond to some other state. There are many states possible here. And the similar thing can be done for RHS, and it is given by this.
Many states will be 27?
It won't be, no, it would be n cube C2.
Oh,
because
of identical nature.
No, the level we are at, see the total creation operators are n cube by 2, right? And at level 2, we have 2 creation operators. We can choose 2 creation operators, which is n cube by 2 C2. These are the number of states which should be possible.
I understand. But in terms of representations, it will be this times, there are 27 possibilities.
Yeah, there are 27 or something possibilities, but many of them are zeros.
Fine.
Trivial, like that I'm going to explain.
Yeah.
So there's no trace there.
Yeah. So it would be 3 times 3 times 2,
Oh, sorry.
18. Yeah, and also we can see that the left hand side has, the right hand side has only a subset of the possibilities which are possible here.
Either 0 or 1, this kind of thing. Eigenvalue is either 0 or 1.
No, it will be, for example, just by comparing, we know that this and this are eigenstates with eigenvalue 4n, and these things are eigenvalue minus 4n, and rest of the states have a 0 eigenvalue. So, and yeah. Sure. Oh, n is coming because of the trace here. Like the trace definition, we have some n somewhere. Yeah, that's an overall factor. There is an overall factor of n somewhere. Yeah, as you can see here also there is still a spectral mirror symmetry because one eigenvalue is at plus 4n and the other is at minus 4n. So, this procedure can be done for any representation, at any level, but as you go bigger and bigger levels, finding the representation itself is hard. So, yeah, now this is what we said, all the leveler states are given by irreps in this, but the problem is that one thing we didn't take care, we should take care is that these are fermions and there is this symmetry. So not all the possible irreps are non-zero, some of them are trivially zero.
You should be taking the tensor product with Fermi statistics.
Yeah, exactly, yeah. And that seems to be a hard problem.
Use Fermi exponents here.
Sorry?
Fermionic statistic exponents.
Oh, okay. Okay, I can talk about I'm not aware of that.
Simple things, but
Oh, okay, fine.
the characters.
Oh, achha. So first let me tell you an example. Like at level r equal to 2, these are the only things which are non-zero. Like if you have any other thing, it is simply 0. That state is 0. So that is not, I mean, yeah, these are the only possible eigenstates, like, and the rest of trivial is 0. There is no comparison or anything because it becomes 0. And so how do we find which of the representatives are non-zero? Like first of all, we write at any level r, this is the state. I'm ignoring the pluses here, and also I'm not writing the Clifford vacuum, but it's the same thing again. And to define the standard approach in the literature which we found is that we start with denoting I1, J1, K1 as some capital index I, and then we see that this entire thing is in a completely antisymmetric representation of SR. And to find the antisymmetric states at level R, these are given by R1, R2, R3, such that the inner product of R1, R2 and R3 contains the antisymmetric representation of SR. Like, let me explain like what is inner product. Generally, whenever we take a product of two young tableau, like say this belongs to S2. I mean, just Sn are like permutation groups. I'm just talking about in terms of permutation group rather than Lie groups. This is S2 times say some S3. The resultant things we get are representative of S5. This is the usual thing you do. But the inner product, by inner product I mean that you take something like say S3 times S3 and you expand it in terms of representations of S3. This is one of the products that you can define with respect to the permutation groups, and this is the thing we need. So for example, if we want to find the which are the representations which survive under this Fermi symmetry, we just take this is R1, R2, R3. Each of them belong to say SR. We take an inner product. Say I denote inner product by some this, and we see whether this has R boxes. We see whether the inner product of these three will contain this representation or not. If it contains, then the state is non-zero under the Fermi statistics. Otherwise, it's trivially 0. This is a technical detail, but and also we proposed some alternative way to find these antisymmetric states. And again, as you go, as the levels increase, this is we don't know. Like I mean, it becomes quite complicated. And also the degeneracy you're talking about, it starts from say level 5. Like anyway, yeah. For example.
Sorry, I'm going to ask an embarrassing question. You're at level 2, so you're acting with two creation operators of fermions. So why aren't each of these creation operators in the fundamental?
Each of them are a fundamental, yes.
So what?
But the total, I mean, like.
So what did you tensor? Sorry, if you went to that thing with the 18 different representations, the slide.
Yeah. So this is a tensor product of I1 and I2.
Okay, but why were I thought the idea was that you're supposed to take that times that. No.
Yeah. Which times which? Sorry.
Entry in the bracket is separate ON.
Each entry is a
Separate ON group. Yeah.
ON group. This is the RHS of tensor product of two triplets.
Yeah.
Two triplet of these.
Yeah.
Yes.
Thank.
Yeah.
Thanks.
Yeah. The degeneracy you're talking about starts from like if you're taking 5 boxes in each. Until then, there is no degeneracy. So we don't expect any irrational eigenvalues until that point. I think until that point, everything should be integers, I think.
So in the case of two guys, it just has to be completely antisymmetric, right?
Yeah, that's why only these survive.
Yeah. Each of your products under interchange were either symmetric or antisymmetric.
Yeah.
You just choose an odd number of antisymmetric.
Yes. But yeah, this is easy to see at 2 slot, but 3 slots and all, we have some indices which don't have any symmetric properties.
Right.
Why can't you trace?
Hmm?
Why can't you trace there in the first one?
Oh, you can. I mean, like I mean, this is just an example. Like, yeah, you are right. Like everywhere there should be a plus trace here.
Whenever there's symmetric,
Yeah, there's a plus trace. Yes.
except for
Except for the last one. Yes, that's true.
So, till this stage at least, it looks like it's easier to work with fermions themselves instead of writing them in terms of representation.
No, but see, for example,
You know, the Hamiltonian is diagonal in these.
yeah,
these
that is one. Yeah.
That's something that
And also, like if you want to find the eigenstate, this will be in this messy form. Like for example, for this simple thing, there is this messy form. So if you are putting more things there, it will be like very big expressions you have to deal with. Yeah. One more thing I want to tell about is that if you take the last group to be O2, like we take a tensor model with On times On times O2, then any generic state is just given by this. Like the last one, the last index is only 1 plus. There is no other index. So I'm just writing it as plus. And here finding those states, I mean finding the antisymmetric states is easy. They are just given by R1 comma R2, where R2 is R1 transpose. Like for example, at level 4, these are all the possible antisymmetric states. Only these are the only non-zero things under Fermi statistics. Everything else is 0. So, yeah, for example, here you can see that this is the transpose of this is the transpose of this, and so on. I mean, that is at least as far as I know, it's I took it as a fact that if you take some R1 transpose, this will always contain this antisymmetric representation.
it's because there are as many symmetric and antisymmetric forms. You want the whole thing to be completely antisymmetric.
Here that seems very intuitive, but yeah, that's
So
true.
suppose take the first case. It's completely symmetric in the first ON, completely antisymmetric in the second one. Now, the first one is fine. Now let's look at any one of the others. It's roughly the idea is that for every symmetric thing, you need the other one to be antisymmetric.
Antisymmetric, yeah.
That's true with 4 boxes, right? If you have trace, for example, again.
Trace becomes more complicated here. That's why I didn't put traces, but traces become real. I mean, like that's the extra complication we have.
So you always want to work with 4 n box.
Yeah, I mean, I know the example I've given is for SUN times SUN times SUN. If you have ON, you need to take traces out from everywhere. So yeah, but
Then your rule doesn't work.
yeah, I mean, to find the eigenstates and all, we need to find the traces. But I'm just giving an example here. Like, so what happens at ON times ON times O2?
You know, your discussion of level rank duality, something like that. Yeah. Because you're making fermions out of NK tensor. States out of NK tensor. Symmetric times antisymmetric. That's basically level rank. Yeah.
Provided we know that it's supposed to be
I'm just saying the pairing. That if you have to pair in NK fermions, you'll have to pair a representation of one kind of SUN with another kind of SUN. That will be.
Yeah, one thing I want to emphasize here is that finding the antisymmetric states are easy for ON times O2 is a very well understood thing. As compared to say ON times ON, like there is no such simple formula, like it's a very complicated thing. So.
Maybe this is a stupid question. So I don't see, for example, in the second one, how the total thing is antisymmetric. Is it?
Oh, it is.
The two fermions that are going down there are going to
In the
right
here, yeah.
there.
Say for example, this I fill 1, 2. This I'll fill with 1, 2.
I see. So I can have an assignment in which these two become horizontal. And those
Exactly.
horizontal guys become the two verticals below.
Yeah, that's
I
true.
see. Okay, I can do that. Yeah.
Because you have to, I mean, this is representing some tensor contraction.
Yeah, that's true, yeah.
So, you choose the one that will make it.
Cool. Nice. Thanks.
And also this, for example, if there are only 2 slots, there is never any degeneracy. Like everything appears only once. Like you are talking about degeneracy, right?
Yeah.
That happens only in the 3, starting from the 3 slots. Here there is nothing. So this is probably like a very rough way to see like why all the eigenvalues for On times O2 are integers. Like I don't have a precise understanding, like, I mean, like what are the eigenvalues and all. I think this is one way to see like why all of them are integer eigenvalues. This is also argued by Klebanov and all in one of their papers.
So I can see about degeneracy, but where
I mean,
where
because
are eigenvalues coming from here?
yeah, because we are finding the eigenstates by comparing the representations, right?
Yeah.
And then the eigenvalues are also coming from, like, there's some coefficient on the left hand side. I'll show you. For example, here, say we have some representation here that will have some coefficient, and this will have some. This will have the same representation that will have some other coefficient. Yeah, at least by comparing these two, we can see that those are just given by rational numbers. Sorry, I meant rational numbers when I said integers. So we can see that all the eigenvalues should be at least rational numbers for sure, but integers I don't know how to argue about. Yeah. But Klebanov and all argued that they should be integers in one of their papers, but with some other technique. So it will be good to see like how to start from here and find that they are integers. Like that's one small step to do before understanding the spectrum. Yeah. Now we go to the finding the singlet spectrum, and for example, we can show that all the things with odd n does not admit any singlets. That I am going to show it you argue using the mid-level condition. Hence, we discuss the even n case, and also we consider uncolored models in this.
Sorry, when you are creating the states with this plus, right, instead of minus, then in terms of the Z2, inside the third one, you always have plus sign. Also, two of this plus. Sorry, yeah, go ahead.
Yeah, yeah. So also one more thing we can show using the formulas I am going to discuss is that, for example, the this model and this model under the gauge of On and On times On does not admit any singlets. That we can show. I mean, I'm not going to talk about much about this. We can discuss it later if you want.
Sorry, I still want to ask my question.
Yeah.
So when you have these states here creating with these pluses, you will always have baryon charge increasing, right? How are you going to have singlets in terms of the last ON?
Oh, yeah, I mean, the last singlet you can only make using epsilon tensors.
But that's SU n by 2 singlet.
Yeah, I mean, the final singlet would be a combination of those singlets. It's like some linear combination of SU n by 2 singlets will give you a ON singlet.
No.
It won't? I mean,
So
at least.
if you have SU n by 2 singlet, if you talk about its charged under the relative rotation of the two.
Yeah, but one more thing to note is that the Clifford.
Always positive.
No, the Clifford vacuum we are defining. This also transforms non-trivially under ON cube, the last ON.
What is the charge of that with respect to baryon?
From the
That I'm.
That's why the
Pause.
mid-level.
Yeah. So to find the singlet, we impose this condition QA acting on any singlet state equal to 0, where QAs are the Noether charges. So these are the constraints we solve and find the singlet states. For example, for the uncolored model, these are the Noether charges.
Sorry, just pretty good.
Yeah.
Okay. The statement that psi I del T psi I has no singlets is simply that in that model there is just a spinner, right?
Yes, yes.
So of
That's
course
true.
there's no singlets.
Yeah, yeah.
The statement that the two guys, that's less obvious to me. That's
Yeah, that I can tell you after discussing the formula. I mean, I'm not discussing some aspects of it, like so. Probably it's difficult to explain it in the talk. Like I can explain it later.
There's no simple statement.
I don't know. It is like we just see that from these charges, one of the charges doesn't annihilate it. So it is never 0. So. Yeah. Also, you start with the third charge, and from there you can show that all the singlets are n cubed by 4th level, which is called the mid-level condition, and this rules out the possibility that the odd n will have any singlets, like because n cubed by 4 is a fraction and it doesn't. I mean, that doesn't make any sense.
But what is the canonical choice for the Clifford vacuum?
No. I mean, why does that influence any the singlet
So
states?
that's where this is coming from.
Yeah, this is coming from there, but I mean,
You are saying the
I think I'm not sure of that. It is charged. That I know.
At level 1, you will always have charge 1. With respect, let's just talk about a particular U1, which is the U1 which relatively rotates differently, the 2 SUN by 2 blocks. You also want charge 0 for that in particular, because you want a singlet sector. Now every level is just a plus sign, so on, right? So you have M levels, you have charge M. You want a charge 0. That will happen only when your Clifford vacuum has some charge which is compensated by your creation operators.
Yes.
So whether or not that level exists depends on whether Clifford vacuum has the
principle will be that you want your final spectrum to be in representations of that last one.
But
yeah,
it's not totally obvious that then this is the condition for the Clifford vacuum.
Yeah, I mean, that might be one of the reasons like why we are not able to completely solve the third charge. So
it probably will be, because when you flip it, having completely filled and completely empty should be symmetric. And that will fix it.
But it's not,
yeah, it's not obvious at least. Like the first two are very obvious how to find the singlets for, singlet structure, how to fix the singlet structure from them. But the third charge is difficult.
But it seems likely to me that you will not, any other choice will not allow representations to arrange in representations of the last one.
Yeah, this is something that is familiar from.
I was thinking in supersymmetry representations we often do the same. Like when we quantize supersymmetry just to get graviton, you've got an algebra and then you've got a lowest state. And you choose it to ensure CPT.
Yeah, CPT I agree, but in particular because subgroup is the same.
Yeah, that's what I was thinking. But
Like monopole operators also.
yeah, you do. Right.
Yeah, here we find the singlets for n equal to 2, and for n equal to 2, these are the Noether charges. And from the mid-level condition, we can show that all the singlets are at level 2 because there are 4 creation operators in this case. And imposing this constraint.
Sorry, just to say, under the U1 that you were talking about, and you take any representation of O, it's probably true that the spectrum is symmetric under that U1. And for every state with plus, there's a state with minus. So that uniquely fixes.
Yeah, and all the singlets for this model for n equal to 2 will be at level 2, and imposing this constraint like for the rest of the 2 charges.
I'm sorry, in all this discussion I missed where you got your mid-level. Could you just go through that slowly?
These are the Noether charges for the uncolored model. And you take this charge and put k2 equal to k1 plus 1 and sum over all the k1.
These are the charges for the 3
ON cube.
The 3 ON cubes.
Yeah. And you take this large charge and you make this substitution k2 equal to k1 plus 1 and sum over all the k1 odd k1s. This immediately gives you that all the singlets should be at n cube by 4th level.
I see. So the summing over k1 equals k2 is exactly doing what Abhijit wanted, right?
Oh, is it?
It's just counting the number of pluses.
Yeah, exactly. Yeah.
Okay.
Yes.
Summing over, so you're only using Q3?
Yeah.
K2 plus K1 plus 1 is just implementing the pairing that we did.
Yeah,
Raising and
that's true. Yeah.
Raising and lowering, and then you sum over all of that.
Yes. So it is only coming. The level condition is only coming from the third ON, like which we broke.
And it seems to me that he's just counting how many.
Yeah.
Right?
How many pluses? Yes.
It's just that. Yeah. So all, as Abhijit said, it comes completely from the assignment of the vacuum.
Yeah, that's true. Yeah, now we are going to talk about a simple example where we find singlets in n equal to 2 uncolored model.
just before that,
Yeah.
you had an equal 0 set of states, right? Where does that appear? At what level does it appear? At each level there are
No, at every level there are some 0 eigenstates. Yeah.
So that spectral mirror symmetry that you had acts very non-trivially on this basis.
I don't know whether that operator commutes with these Noether charges. That I'm not sure. That I can check. I mean, I'm not sure. Yeah, possibly it does, because all the singlets we found, I mean, like here or in the other case, other non-trivial example we are talking about, everything is spectral mirror symmetry. It has that symmetry. So I think it should commute, I think.
There are singlets at arbitrarily high energies also.
Yeah, yeah, yeah. For example, you can always, yeah, here also, these two states are the singlets in this model, like n equal to 2 uncolored model. These two correspond to the ground state and the highest energy state.
But so you should probably start from the beginning of the
Oh, okay. So for n equal to 2, these are the Noether charges, and from the last charge, we can show that all the, I mean, the mid-level condition, which shows that all the singlets are at level 2, because there are only 4 creation operators in this. And imposing the other 2 constraints, you see that these are the only 2 singlets possible in this model. The Hilbert space dimension is like, I think, 16 dimensional, and only 2 of them survive under the singlet condition. And these correspond to the lowest energy, I mean, the ground state and the highest energy state. The ground state and the Clifford vacuum are completely 2 different things, so don't mix them up.
Now, one question,
Yeah.
which is sort of general. You broke the symmetry of O n times O n times O n by choosing one O n to
Yes.
define your.
Yeah.
Now, you could have done it with any of the other 3.
Yes.
Can you use that to simplify your finding of the singlet set, for instance?
I mean, break instead of the third, break the second one, for example. That's what
you
you're
know
saying.
that in this representation it's this.
Hmm.
But you know that in all the other representations something similar.
Yeah, yeah.
Could that be used to help you?
Possibly, like that is one way we thought about, but as I was saying, like finding the singlets with respect to the last charge, if it is not equal to 2, is hard. Like we don't have a particular algorithm or anything.
Okay.
So that is what we wanted to do, just compare the things to make things simple.
Yeah, but they're not simultaneously diagonal.
Yeah.
So, but you have to be clever.
Yes.
So this is just 1 epsilon for the last guy, right?
Yeah. Yeah, I'm going to write the states.
No, epsilon is just
The last one.
so
Oh, here the last one is easy because there is only one charge. There's only one creation operator, and
the last one is only 1.
yeah, that's right.
And then on the right, on the other guys, you want
Yeah, other things are just given by this. Is delta I1, I2, epsilon J1, J2, and the other thing is epsilon J1, J2, delta I1, I2.
Epsilon figure is very small.
Hmm.
You write epsilon.
Sorry. Yeah. So it is just both the states are just given by this. Say psi I1, J1 plus psi I2, the same. So these are the 2 states that I have written there. And now we can talk about singlets in the Gurau-Witten model. This is a generically a hard problem because the symmetry group is much bigger and the Hamiltonian is also complicated. But if you consider n equal to 2 in this case,
Meaning when the fermions are not identical.
yeah, yeah. If you consider n equal to 2 in this Gurau-Witten case, the advantage is that the spectrum is non-trivial and the spectrum is like 65,000 dimensional, and if you gaze it, we still have 140 states left in the gaze spectrum. And now we'll find how to find those singlet states. First, we start by introducing a basis. Like as before, we define the creation annihilation operators like this, but here we have 4 of them because here A runs from 0, 1, 2, 3. Yeah.
If we don't finish number 15 minutes, we'll have trouble with getting lunch.
Oh, okay. I'll first. Yeah, here we define these creation annihilation operators, and then we define the Clifford vacuum as usual. And this is a symmetry group in this case, and the corresponding Noether charges are given by this. And again, there is a mid-level condition here, which means that all the singlets are at n cube level, but there is extra constraint that n cube by 2 should belong to colors 0 and 3, and the rest of them belong to 1 and 2. So this is the mid-level condition here, and now we specialize to n equal to 2 model. In that case, these two charges just give the mid-level condition. There is nothing more to this. And from these two states, we see that any generic singlet state should be of this form. If you see, there are 4 corresponding to 0 and 3, and 4 of the creation operators corresponding from 1 and 2. And now we need to solve the other 4 charges. So, yeah, basically the entire discussion sums up to this statement that all the alphas should be made up of epsilon and deltas corresponding to the first 4 ON groups. Like, yeah, for example, this alpha, for example, can be delta I1, I2, epsilon I3, I4, and so on. Like, it should only be made up of deltas and epsilons. And this is a generic statement. Like, these 4 charges, as we have seen here also, the singlet part, the singlet constants coming from them just tells you that this alpha is made up of only epsilons and deltas. And yeah, now using this constraint, we can list down all the, using the mid-level condition, using this and the fact that it's only made up of epsilon and deltas, we can list down all the singlet states. The next thing is that we need to act the Hamiltonian on each of the singlet states and then find the eigenstates. And that is conceptually simple, but the expressions are somewhat tedious. So, one of the things that reduces the number of computations is the discrete symmetries of the Hamiltonian. For example, in the Gurau-Witten model, if you exchange colors and all, those are the discrete symmetries. And if you exchange, say, any pair of color, the h goes to minus h. So, these kind of symmetries are there. So, we can just use them to reduce the number of computations in this. So, if we do all the computations, then this is the eigenvalues we found. Like, this is, for example, this is the ground state and the highest energy state. This is unique, but rest of all of them still have degeneracies. Like, even though we gauged away the entire group, but still we have some degeneracies. And the degeneracies of first 4 we can explain completely by identifying the discrete symmetry operators, but the rest, the last 2 we can explain only partially. Like, some of them, I think there might be some extra symmetries which we still need to identify. And also, if you plot the spectral form factor, there are very rudimentary signs of chaos, because I'm saying very rudimentary because the number of independent eigenvalues are very few in number. There are only 11 in number. So, we can't really say anything much about chaos.
So, these degeneration which you couldn't explain, could they be due to accidental symmetries?
Yeah, possibly, yeah, I think so. Yeah, I'm not sure. I'm not completely sure whether it's accidental or is there any other symmetry which we miss.
So, what did you say? The total number of independent eigenvalues are 11 or something?
Yeah, if you just count the number of values, those are only 11 in number.
So, what are you trying to do? You're plotting that against a curve?
The spectral form factor is simply a computer like this. I'll tell what. Z is a partition function. Z is a partition function, and you compute this quantity and plot it against time for a fixed beta. And the claim of Shankar and all is that for chaotic systems, the spectral form factor will have this form. And we roughly see this form, but it's not very distinct.
I thought that the denominator was not mod z beta square, it was z of 2 beta.
No, I think it should be this. But I think you might be talking about the height, which is given by, I think, z of 2 beta by z of beta or something like this.
Yeah, the asymptotic thing.
Yeah, asymptotic thing is given by this.
That's not what you're normalizing by. You're normalizing
No.
by z of beta.
Yeah.
I see. Okay.
Yeah, that's it.
And you're taking the sign of chaos as what?
For the if you plot this quantity with respect to time,
Yes.
for a fixed beta,
Yes.
then it should have this. It starts with some point, goes down, and then increases and saturates at a plateau.
The whole shape.
Yeah, the whole shape.
Chaos exponent?
I don't.
This is more like a 2-point function.
Yeah, it's a 2-point function. Yes.
So it's just some qualitative.
Yeah, they have some argument, like they compared the SYK and the random matrices. They say that both of them will have the same shape. That's their argument.
Yeah, so but maybe a more straightforward thing to do is if you have the ensemble of matrices that you expect, you
But
just take your eigenvalues and plot them.
yeah,
against
but that's what I'm saying. Like there are only 11 eigenvalues, so we don't know.
I think that there's no need to introduce time into this.
Yeah, possibly.
If you just know what row of you expect, just compare against that.
Can you say what you expect for chaos, the density of the spectral thing?
The spectral form factor should look. Oh, there is something called level repulsion plot or level spacing plot which you plot, which is like you take all the eigenvalues in ascending order, and you take the difference between each of the eigenvalues, nearest eigenvalues, and then plot it as plot them. And this is a spacing of eigenvalues. And for chaotic systems, it should be something like this. And for integrable systems, it would be like this. So this is the distinction. Yeah. Also, one more thing is that until now we found all the singlets by demanding that Noether charges annihilate the singlet states, but Noether charges only takes care of the continuous part of the group. So until now what we have found is that SO2 power 6 singlets, not O2 power 6 singlets. If we instead gauge it by O2 power 6, the number of singlet states reduced to 6. And the spectrum is simple. There are only four zero eigenvalues, and the other 2 eigenvalues are given by this. And these are the lowest and highest energy eigenstates. For clarity, this is the ground state for us. And this plus or minus correspond to plus or minus 2 root 14. Yeah, this is the ground state is one of the most complicated things. There are other things which are comparatively easier. And now I'll conclude with some future directions. Like one way, our method has potential to be generalized to models with arbitrary n.
And can you tell me what is the main, once you found the spectrum, the main thing you want to do is to check whether there's chaos or not?
Yeah.
What are you going to use the spectrum?
Yeah, mainly for chaos. We want to see whether there's still chaos left in it or not. But the problem is that if you want to do it for uncolored models, we should at least do it for O6 cube. That is the thing which has sufficient number of eigenvalues to see whether there's chaos or not. But that is yeah. Klabanov and all recently has done for O4 cube. They found some things.
Using similar methods?
No, not similar methods. They did it numerically. They use some Lancerus algorithm. I forgot the name. So some algorithm.
What do they do? I mean, what's the stuff that they compute? So you have said that you have this.
What Klabanov will do is that they find the singlets in O4 cube uncolored model, all the singlets. There are only 36 of them, but they found.
I thought you were saying that they also look at thing of chaos. I see.
Oh no.
And then they find the eigenvalues.
Yeah, numerically, yeah. Yeah, the method we described is that in principle should work for arbitrary n, but the things get tedious really fast. So as I was saying before, we know how to solve, for example, if you consider uncolored models, there are 3 Noether charges, Q1, Q2, Q3, and we know how to solve 1 and 2 completely for any n. But the third charge is computationally intense. For example, if you want to solve it for O4 cube, we need to first find antisymmetric states at level 16. This I don't know any easy way to find. There is no proper algorithm or anything. So I don't know exactly how to do this. And also there is a simpler problem to try before trying to solve the most general problem. For example, as I was talking about before also, if there is an O2, the last charge only gives you the mid-level condition. There is no other information in it. So, and also we know, apart from the last charge, we know how to solve the remaining things. So in principle, we can list down all the possible singlets. But finding which ones are independent seems to be a difficult task. There are many deltas and epsilons in multiple ways can lead to the same singlet. We don't know how to identify the independent things among them. And these papers talk briefly about it, but and they use it for counting the number of singlet purposes.
So there's a formula for number of singlets.
Yeah, but these people only count for SUN cube or something. So yeah. So they only have deltas. No, they only have epsilons. Like, yeah. Sorry, maybe yeah. There's some difference basically. Yeah, these are the two directions we would like to report it on the future, and these are the various references I used. And thanks.
So I'm asking again, just in case you happen to know, but how many singlets are there? Let's say, I just want a rough estimate. Is it like power of n or exponential in n?
It should be like roughly it's like 2 power n cube, 2 power n cube by 2 minus some n square by 2 kind of n square kind of thing. I don't know how like.
Yeah.
So it is like.
The number of singlets won't change.
So minus n square. This is, if I remember correctly, this is the form at large n. Like this is asymptotic formula.
So it's such a large number.
Yeah, it is a large number. Yeah. Like that is why, like for O6 cube, the number of singlets goes like probably million or something, order of million. Clavinov has done it. Clavinov and his collaborators. Yeah, the problem is that O4 cube has only 36, and O6 cube goes to million. So there is no in between thing which can actually solve.
Why does it surprise you, Shiraz? I mean, what did you expect?
Somehow it felt like it's not so easy to make these signals. I don't know why.
Oh.
But yeah, I had expected a slower growth than the.
No, the problem is that. Yeah, I'm not sorry.
Yeah.
And,
No,
really
I'm
is-
just probably a wrong image. I mean, what I mean is this. Suppose you take a spinner and you break it up into 4 ONs like a sum, not a product. And you ask for a singlet under any one of those, there are no singlets. It didn't seem so easy to make singlets out of spinners. But of course, it's a very different problem.
If you forget about this creation annihilation business, it just considers operators. It just want ON to the power 3 singlets in the multiparity fermion inside the fermion transform, the dry fundamental. Then the interaction operator was 1. Then you can do all sorts of convention to make various things.
Yes.
Dry fundamental inside.
And then multi-party.
Yeah.
Hmm.
Some of those operators would be annihilation operators, so I guess we would want to count those.
Even in the SUN,
Hmm.
so in the model where it's SUN cube,
Mm-hmm.
and your fermions are just in the fundamental, or the fundamental and anti-fundamental?
I think it should be fundamental and anti-fundamental.
And anti-fundamental.
Because you can't write a.
But if you have just SUN cube and only fundamentals,
Then it might be hard. I mean, I don't know how to write the Hamiltonian in the first place, right? Hamiltonian
I
is
see.
yeah.
It's related to what? Yeah. Thank you.
If no further questions, this time.
Thank you.
Sorry, one last question.
Yeah.
It's a question Abhijit asked, but I'll ask it again. From the spectrum, you know the spectrum of the eigenvalue, maybe you got the answer. From the spectrum, can we read off somehow the chaos exponent?
Yeah.
If you know the whole spectrum of the model, you know a lot about the model.
I mean,
What is the way of reading off the chaos exponent from?
you mean only eigenvalues or eigenvalues and eigenstates?
Let's say to start with only eigenvalues.
Probably,
Eigenstates
yeah.
is some
That
representation.
that we thought about, but we didn't. I mean, we didn't find any answer actually. That one for that question. It's
even that whether it's maximally chaotic or not. I mean, there's something about the Schwartzian determining some part of the spectrum, right? I was wondering if you could pull that up. Do you know what I mean?
Yeah, that's the
end. So suppose I know the exact eigenvalue spectrum.
The vague thing here is that the rho of E should resemble the random matrix, but that's too vague.
And that would work whether chaos was maximal or not, right?
Yes.
Yeah, I think.
Yeah. That would work.
Suppose I want to know the value of the coefficient.
Yes.
Some people talk about the nature of the eigenvalue distribution. They define chaos by that. That has to be related to this other way of defining chaos. This is the same question. Know these.
Exactly.
Yeah, according to one of my collaborators, he is saying that these two are like the OTOC and this random matrix behavior are coming into different, like as I was telling before also, I was mixed up with time. He was telling that this OTOC is like very dependent on the system, whereas this random matrices thing is completely independent of the system. Like it doesn't remember any details of the system. So he's saying that these might be two different regimes, might be two independent definitions of quantum chaos. So I'm not.
He talks about the low-lying part of the spectrum.
Yeah.
And spacing is talked about the real part of it.
Is it true? I mean.
The chaos relating lower part to higher part seems more like an integral.
Yeah. But suppose we're not asking as ambitious a question as that. I'm just giving you the whole spectrum. I think from that rid of chaos exponents. So you have high energy, low energy, everything.
Yeah.
You can take to insert complete set of eigenstates and so on, try to manipulate it so that it's
Possible.
Yeah. And there's some matrix elements which you take to be order 1.
Yeah.
matrix elements.
So let's say you've got 4 operators.
Yeah. In each evolution, you just place by into the int. This too simplistic. I don't know whether this is useful. Try to manipulate that expression spectrum.
No, but you will have the matrix elements of those operators in the
Yeah,
regime
and
against
local
X.
operators. I mean, there is no evolution there. There is a fixed number. That's what you say.
Yeah.
The matrix. Yeah, you should just
So
take
in the
order
sum,
out
they
one.
will all hang around,
Yeah,
and then you'll have to make some answers about what those matrix elements are.
because there also the choice of this V and W is just arbitrary, right?
It is arbitrary, but you still have to say something about them.
Oh, with the all line. Yeah. Matrix elements with respect to all line.
So what people have diagonalized the SYK Hamiltonian very efficiently, right? What have they used the answers for?
Mainly
People are
the.
able to, this is right, Gautam? People are able to just diagonalize this very fast. And
Yeah, so
why do they do that? What do they want?
yeah, I know that the edges have the square root behavior that they have verified. That you can get from theory, analytically by doing the one loop determinant using the Schwartzian modes.
Yes.
And that square root has been verified.
Yeah.
But
And also, some people have done this ETH, like they showed that it is ETH system. The eigenstate thermalization happens here.
Right. That is
Right,
some
yeah.
people have used it to show ETH.
And also this paper by Shankar and all, where they studied this spectral form factor. Like they argued that this part of SYK from here to here, like this part of SYK is very much similar to random matrices, but the initial part is controlled by this Schwartzian, so it is different for random matrices and SYK. So yeah, that is like, yeah.